Okay, so let's start. So this is a response for simple harmonic motion kind, undamped free vibration response. So that is, and our intention is to avoid the natural frequency F naught with the driving frequency. Means that is when natural frequency is coincide with the driving frequency, that is the phenomena called resonance will occur. So this is the resonance condition. So the point of resonance is here. So this diagram shows the natural frequency of the material, that omega over k and radical, no, k over m. Omega n is equals to radical of k over m is this one. And this is a driving frequency or excitation frequency. So this is just simple recap of the previous discussions, most discussions. So when we are providing damping to the system which is undergo free vibration, then we can find this kind of response. This is a response for damped vibration kind. Okay, so this response of damped vibration in case the decaying of the motion. Okay, initially it is with high amplitude. Okay, it oscillates like this, and then finally it will start to decay. In most cases, the decay is kind of logarithmic decay. Okay, so this is a time graph, and this is the response graph. So the maximum amplitude considered 20 unit at this point, and finally it goes to diminish here. So this is a response of damped vibration. And it is gradually decaying. Yeah. So this line indicates that the way how it is decaying. So these are some of the graphs that we can obtain because of damping. As we increase the level of damping, we can reduce the higher amplitude. This indicates the amplitude will go infinity. This two blue line, not blue, but two almost green lines indicates that if we leave the system with no damping, then the amplitude will go to infinity and the resonance will occur on the system. So to avoid that, we have to provide a simple kind of damping. So as the level of damping increase, the amplitude decrease like this. Okay, this is the amplitude of motion, the amplitude of motion. So it is like that. So we have tried to see the free vibration condition, that is when zeta is equals to 0. We have seen overdamped condition when zeta is greater than 0. Underdamped condition when zeta is less than, not 0, but 1. I mean, zeta less than 1, greater than 1, and exactly zeta is equals to 1. So zeta is equal to 1 means critical damping condition. So it is similar to that. This is the situation similar to that. Okay. So this displacement axis and the time axis. So considering this as a equilibrium position, so this is the way how underdamped oscillation will perform. So this is underdamped condition. This is the condition which we discussed in last class. Okay, so the damping is under, then it oscillates like this. Finally, it will decay with time. Okay, so this shows very stiff kind of failing is showing the overdamped oscillation condition. This is overdamped oscillation. This indicates underdamped oscillation. And another, we have a critically damped condition like this. This is critically damped condition. So returns to normal quickly. That goes normal quickly. This one is kind of a stiff graph. Okay. So this thing, the way it is failing is logarithmic also. Yeah, so what is the effect of resonance? Our intention is to avoid a resonance still. What we are dumping is to avoid unnecessary oscillation or to avoid the resonance, the motion of the vibration of system without going to damage the system. If we leave the system with high oscillation, obviously the system will or the machines will immediately break down and will not function properly. So what are the effects of that resonance? So there are some positive effects and negative effects, but the negative, let's see the negative effect of resonance. The positive one is we can get sound, some loud sound from the different kind of music instruments like the trumpets and other things. The worst effect is the collapse of bridge. So this, for example, bridge can easily collapse because of resonance. For example, you can see the wine glass that break because of the opera. One of the opera singers singing the song near to the glass, and the glass is because of the resonance effect, that the coincidence of the natural frequency of an object with excitation frequency, then the glass will break into pieces. The narrow bridge in USA in 1915s has but happened collapsed because of resonance. That build didn't work even for long period of time. So these are some of the worst scenario of the resonance. So these are related with those things. Okay. Soldier need to break. Actually, one of the singer that the glass breaking happened because of the natural frequency of the singer and the natural frequency of the material of the glass coincided. So then immediately it will break down into some piece of. Another is Tacoma Narrow Bridge, which is break down because of a simple kind of marching or this wind effect. So these are kind of damping systems. For example, we provide some shock absorber to the tire of different vehicles, like in the case of aircraft, there are shock stratus are there. Okay, this is kind of shock stratus or shock absorber. Okay, tire is also having, it is dissipative power. It can dissipate. So this is a simple representation of shock absorber, that piston with some kind of oil. Okay, viscous oil is introduced into here that helps to eliminate the intensity of vibration. So these are means for shock absorption. Okay, so this is just free vibration, no damped vibration case, which actually the damping is under damped vibration condition is like this. Okay, and this is the condition of resonance. This is one of the peak oscillation kind. So our aim is to avoid such kind of peak oscillation with this yellow color. The blue color will give us such underdamped condition, and large B, this black color represents appropriate kind of damping. So it gives us like that. So here we can see underdamped oscillation, critically damped oscillation, and overdamped oscillations. Overdamping is also not as such good. And underdamping also exhibits further oscillation to the system, so that we have to provide an appropriate kind of oscillation. So the main intention here is to avoid this dotted line condition. This dotted line condition represents the occurrence of resonance because of the coincidence of the natural frequency with the forcing frequency. The natural frequency is the frequency of the material itself, that radical of K over M. but the forcing frequency is externally exciting frequency. Okay, so this should never be coincide. Okay, so that is the method how we can design our system. So there are some energy dissipating mechanisms. So one of the energy dissipating mechanisms is the applying viscous damper. Okay? Viscous damping means the fluid media is used as a damper. Okay. For example, in the piston mechanism here, there is oil. Some oil is introduced into here. There are sometimes we use some ball and other shock absorbing systems. So this oil used as this energy dissipative means. Okay, so that is one of the energy. So the viscous damping system is the rate of change of energy with time, which is dW over dt. W is energy. So time dt is time derivative. So which is equals to force times velocity. As we know, energy is equal to force times velocity. So the dissipative force is Cx dot. Okay, so x dot means dx over dt. Velocity dx means it is x dot. So velocity square means it is like this. So the negative sign here represents, it denotes the energy dissipation with time. From time to time, the energy is dissipating, or that is some means of absorbing energy. So reduction of energy represented is negative sign. Okay, so this is, so dW is equal to C times dx dt, the whole square times dt. So this dx dt means x dot, means it is velocity. And once we appropriately give as x is equals to x sine omega dt, that means the solution for damped oscillation. X sine omega dt is the solution x of t is equal to x sine omega dt. That is solution for damped oscillation. So by introducing this thing, what we can get is the change in energy from time. So look, this is x of t is equal to x sine omega dt. Or we can introduce x of t is equal to x cos omega dt plus some phase angle pi. So by that, we can define this thing. So this process is known as a hysteretic process. So we can show the hysteretic loop here. There is a spring K, there is damper C, there is some applied load here, and the system will vibrate from its equilibrium position without considering the mass. This is kind of demi mass. It's not exactly the mass, but with even the mass, we can consider it. So our system will make such kind of loading and unloading condition. This is called hysteretic loop or spring viscous damper system. So it gives you dW is equals to, you can use the previous equation into integral for time period. One time period to complete one oscillation is 2 pi over omega d. Yeah, so finally, from this mathematical expression, what we can get is pi c omega d x squared. This x is the maximum amplitude. It is amplitude of the system, okay? So we can represent this height as kx is there, CW radical of x square minus x is there. So this is maximum amplitude. This is any arbitrary position in the x, means the oscillation amplitude. So this is a representation how we can dissipate energy using viscous damper. So this shows the energy dissipated that is delta W, is proportional to the square of the amplitude of motion x, the square of amplitude of motion. So this maximum amplitude of the motion. So look, x of t is equal to x sine omega dt. So this implies when sine reaches to 1, it is maximum amplitude. When sine of the sine oscillation is 0, that is mean position. When sine is to the negative side, that is omega dt is equals to 90 degrees, then it is minus. Means 180 degree. No, 270 degree, then it is minus. In 90 degree, it is plus 1 or plus x, because this sine function will not exceed from 1 to minus 1. The remaining is only about the amplitude of the motion. Uh, so does the spring force will do any network over a complete cycle? This is the question from this point. There is a complete cycle. This is called hysteretic cycle or hysteretic loop. It goes in the during loading condition, goes to here and comes back during unloading condition. So this is loading and unloading condition. So to answer this, we can see these equations. Assume that simple harmonic motion equation is considered. Okay, so x of t is equal to this, x sine omega dt, and x dot of t means the first derivative of x of t is equals to omega dx cos omega dt. So this is the equation. And the equation of motion is F is equals to minus CW dx cos omega t, because we have this F is equal to minus Cx minus Kx. So this F is the mass times acceleration. Okay, this F is the mass times acceleration if we consider mass. Okay. So when we substitute the values of x and x dot, F is equals to minus C omega dx cos omega dt minus Kx sine omega dt is the equation from this point. So we can substitute those values. F is there. This is the F value. Minus C omega dt, x cos omega dt minus Kx sine omega dt is the F value. Again, we are integrating it F times x. This F times x dot means force times velocity is the energy. Okay, the energy dissipated in a complete cycle. Complete cycle means completing one hysteretic loop. During that time, you can introduce the F values here, and we can introduce x dot value. So x dot value is this one, x omega d cos omega dt. And F values are CW dx cos omega dt plus Kx sine omega dt. This omega dt is damped natural frequency. This damped natural frequency is equal to, let me write damped natural frequency, okay. Omega dt means omega d means it is related to its natural frequency by this relation, 1 minus zeta. This zeta is the damping ratio times omega natural. So this is the relation. Yeah, omega d is equals to radical of 1 minus zeta square. It is not only zeta, but zeta square times omega n. Okay, so by rearranging and properly differentiating dt, this time domain of representation is changed to frequency domain. Look, here, fx dt. This dt is changed into d omega dt. This d omega dt is the frequency domain. Now I'm changing all the time derivative to frequency derivative. Okay, so all the things will be done in terms of frequency domain. So after changing it to frequency domain and making some simple trigonometric relation, you can perform some simple trigonometric relation. Then after that, finally what you can get is delta W is equals to CW square, CWD square times X square as a whole, 1 over 2 T plus 1 over 2 omega D sine omega dt for this 2 pi to 0 to 2 pi. Actually, this is the limit of omega dt, okay, 0 to 2 pi omega d. Here also in the same manner. Okay, by substituting this value into in the place of omega dt, finally what we can get is delta omega, or energy dissipated, is equal to C pi omega d x square. Okay, so this implies that the spring force will not do any network over a complete cycle. The spring force is out of this calculation. Only the dissipative force only take place. Delta omega consists only the C component, not the K component. K component didn't come into picture here. You cannot find the K components here. After some point, K components are eliminated here. Okay, so the answer is what? Does spring force will do any network over a complete cycle? So what is your answer now? عندك جي ولا هبتش ما بيت እሺ ስለዚህ ማን ነው 12 ማን ነው 11 ተኩል እንነሳ ሁላችሁም ገብታችኋል ለካ ሄሎ ሄሎ
ሄሎ
እየሰማችሁ ነው
አለን ይሰማል
የቀረ የለም እያልኩ ነው
ይሰማል
ስለዚህ ስፕሪንግ ፎርስ ስራ ይሰራል ወይም ደግሞ ኤነርጂ ዲሲፔሽን ላይ ይሳተፋል ወይ የምለው ጥያቄ ላይ ነው የቆምነው እሱን መልስ የምሰጠኝ አሁን ካገኘነው አንፃር ስራ ይሰራል ወይ ኤነርጂ ዲሲፔሽን ሲስተም ላይ ሄሎ
ይቆራረጣል በደንብ አይሰማም
ኦኬ ኢንተርኔት አንስቴብል ይለኛል እኔጋም
በደንብ አይሰማም
ኦኬ ያ ኔትወርኩ ትንሽ ያስቸግራል anyways so does spring force will do any network over a complete cycle can anyone answer this question hello hello ዳዊት
ሄሎ አይ አልሰማኝም ዶክተር ምንድን
ኢንተርኔት ኮኔክሽን ውስጥ
ጥያቄው እኮ አልገባንም ዶክተር ጥያቄው አልገባንም እኮ
እየተሰማን አልነበረ
እንትኑስ ስላይዱ ይታያቸዋል
አሁን ጠፍቷል።
አሁንስ
ኦኬ አሁን መጥቷል። እሱ ሲመጣ ነው መሰለኝ ግን እንትኑ ድምፅ መቆራረጥ የሚጀምረው። እስቲ አሁን ሞክረው።
እሺ ለማንኛውም እስቲ የሚታያችሁ ከሆነ የማይታያችሁ ከሆነ ዝም ብለን ከምንለፋ
አይ እንትኑ አሁን ስላይዱ ይታያል። ትንሽ ድምፅ
ግን
መቆራረጥ
ስላይዱ
ነው ያለው።
ብታይም በደንብ እንትን ማለት አለብህ።
አዎ እኮ እንትን ድምፅ ይቆራረጣል።
ወይ እምቢ ካለን ሞክረውና ሪከርድ አድርገህ መላክ ትችላለህ።
እሺ ለማንኛውም ምንድነው ስፕሪንግ ፎርስ እዚህ ጋር ስፕሪንግ አለ፣ ዳሽፖት አለ። ዳሽፖት ማለት በዳምፐሩ ማለት ነው። ስፕሪንግ ፎርስ ኬኤክስ ነው። ዳሽፖት ኦኬ ዳሽፖቱ ደግሞ ሲኤክስ ዶት ነው። ያን ፎርስ ኢኩዌሽን ውስጥ አስገብተን ካልኩሌት አድርገን መጨረሻ ላይ ኢነርጂ ዲሲፔሽን ስናገኝ የኬ ኮምፖናንት ዜሮ ሆነብን። ኬ ኮምፖናንት ምንም ወርክ ላይ እየተሳተፈ አይደለም። ይሄ ፓርት ወደዚህ በኩል ያለው ኮስ ላይ 2 ፓይ ኦቨር ኦሜጋ ዲ ኢንስቲድ ኦፍ ቲ ብንከተው ይሄን ምን ያደርገዋል? አንድ ያደርገዋል ማለት ኮስ ያ ኦሜጋ ዲ በኦሜጋ ዲ ይጠፋል። 2 ፓይ 4 ፓይም ዜሮም ቢሆን ምንድነው የሚሆነው? አንድ ነው። ስለዚህ ኮስ ዜሮ አንድ ነው። ኮስ 2 ፓይ 4 ፓይም አንድ ነው። አንድ ሲቀነስ አንድ ዜሮ ይመጣል ይሄኛው ፓርት። ሳይን ላይ ግን 2 ፓይ ኦቨር ኦሜጋ ዲ ይሄኛው ፓርት እዚህ ጋር አለ። ልቀጥል ወይስ በቃ እንደዚሁ ነው? ሄሎ ዴቭ። ሄሎ ዳዊት። ዳዊት